Hello, welcome to this video. This is 1B lesson 2. We're going to talk about holes and asymptotes and how we find them algebraically from functions of rational functions. Okay, so our learning intention for this lesson is how to identify holes and asymptotes, and you'll be successful in doing this if you can determine where a function has a hole and identify the x and y coordinates of the hole. In addition, you can write a limit notation for a hole, we'll talk about that, as well as determine the equation of a vertical asymptote, as well as describe the behavior of a rational function at a vertical asymptote using limit notation. So really, two big ideas here. We have holes and we have asymptotes, and we are going to work in this idea of limit notation. So pretty straightforward. In the last lesson, we introduced what rational functions look like. Here's our rational function. Think fractional. It's broken into pieces. And we visually identified asymptotes. Here's an asymptote, okay, at this line x equals 1. And we identified holes. Here's a hole at the location 1, 2, 3, -1. So identifying them visually, pretty easy, but what do I do? How do I identify them algebraically? So here is kind of what happens. Both of these kind of features occur when we have a factor in the denominator. So I'm going to highlight this in yellow. You're going to see if you have a factor in the denominator, that is going to create what we call in mathematics, maybe you want to add this in here, a discontinuity. We'll talk a lot about that in calculus, but we have some disruptions to our functions when we have factors in the denominator. Okay, so what makes it a hole versus an asymptote? How do I know if it's going to be a hole or an asymptote? Well, it depends. You will have a hole at that x value with a factor here x minus a, and I'll show you algebraically how to find this. If you have that factor in the numerator and it's equal to or greater than the multiplicity of the same factor in the denominator. So pretty much, and maybe right here in parentheses, I want you to add this, I want you to add the word match. If you have a factor that matches in the numerator and the denominator, it's going to be a hole, most likely. There's like a 5% chance it's going to be an asymptote. We'll talk about that in a second. Now, if I just have a factor in the denominator, let's say x minus a, and it does not match anything in the numerator, it's going to be an asymptote. Now, if it does, if the denominator factor does match the numerator, but the multiplicity in the denominator is bigger, then it's going to be an asymptote, okay? So we'll kind of work through this here in a second, okay? So let's look at an example, okay? Here's what I want you to see. A rational function, we have all of these factors. What do I have? Do I have holes? Do I have asymptotes? Well, what I want you to see here is at x plus 4, those will essentially cancel. They match, but what I want you to notice is, do you see how that denominator is bigger there? Okay, it's going to survive. So after those cancel, I have an x plus 4 in the denominator. Okay, and because that x plus 4 is still in the denominator, it's going to be an asymptote. It's going to be an asymptote. And what we do is we set it equal to 0 and we solve. So if I were to subtract 4 on each side, subtract 4, we get x equals -4. If you're familiar with like the a, h, and k, it's always just the opposite factor, your h value, always the opposite. So -4 is an asymptote, and you can see that here. Here we have x equals -4. It's an asymptote. Okay, let's move on to the next factor. What about x minus 3? Oh, check it out. Again, they match. They match here. But who kind of wins in this fight? Isn't it the numerator? Don't you guys see we have x minus 3 to the power of 2? So since it's in the numerator, this is going to be a hole. It's going to be a hole. X minus 3, I don't know why I'm trying to put parentheses around that, equals 0. Add 3, you get x equals 3. So here is a hole. Okay, so that's kind of like where they match, but one survives either. we looked at factors that were shared in the numerator and the denominator. What about factors that are only shared once, that don't survive? So here, you guys see how we have a shared factor x plus 1? That's going to be a whole. So if the multiplicity, the count on the factor, is the same or it's bigger in the numerator, it's going to be a whole. So this is x equals negative 1. So x equals negative 1. Okay, the last case that I have for you guys is x minus 5. Do you see it down here in the denominator? It doesn't cancel with anything. It's just by itself in the denominator, remaining factor in the denominator. This is going to be an asymptote. So x minus 5 equals 0. That's going to be an asymptote at x equals 5. And let me label this over here. So here are your asymptotes or asymptotes. And then here are the wholes, okay? So this factor right here, I do want to say this is your reduced factor, So if you ever have to evaluate this function at one of these x values, you'll want to evaluate the reduced function, not reduced factor, reduced function, okay? All right, at this point, you should stop and ask yourself, how do I algebraically determine a whole? How do I algebraically determine myself if we have an asymptote? Okay, ask yourself that question. Okay, hopefully you easily identified what makes a whole, what makes an asymptote. Easy way to remember is if you have a factor that's shared, it's going to be a whole, unless after reducing it is in the denominator. If it's in the denominator after reducing, it is an asymptote. Okay, you can see the x plus 4, that gives us x equals negative 4, x minus 5 gives us x equals 5 as asymptotes. Okay, the next section here is on limits. I'm going to kind of bypass that here. We want to go ahead and look at some examples. Let's put this into practice. So here, example 1, it says for each rational function, find the x coordinate of any wholes. And so what I'm going to do here, step 1, is I am going to reduce the function f of x. Okay, and this will go ahead and help us. So I'm going to reduce in x here, and I still have an x in the denominator. Oh, you know what? I fell into a trap, guys. Let's factor and then reduce. I gotta factor this. I didn't see that coming. Disrupted by all these technical delays. Here we go. X plus 4, x plus 2. Okay, so I just factored this trinomial. I had an x, right? Maybe I'll put this, I'll add this step in. Here we go, x squared x. Okay, we're completely factored. Now let's go ahead and reduce. So I can reduce an x. So in my denominator, I have an x. And then in my numerator, it looks here, x plus 4 canceled out. And then what survives? X minus 2. And then I have an x plus 2. So I really want to kind of do this also from the lens of an asymptote too. Your vertical asymptotes, which I'll abbreviate as VA, are factors in the denominator. Are factors in the denominator. So we're going to have vertical asymptotes from these factors here. So x equals 0, this is going to be a vertical asymptote. We have x plus 2, which gives us a vertical asymptote at negative 2. Those are vertical asymptotes. So I want to outright say that. And then I want to go back to, okay, what did I reduce? Well, I reduced an x, okay, but the multiplicity was bigger in the denominator, so that is a whole. Okay, but I have this x plus 4 here, okay, x plus 4. So wholes from shared factors that do not end up surviving in the denominator. Very important here. We had x plus 4, so I can set this equal to 0 and solve. Take away 4 on both sides, boop, boop, and we get x equals negative 4. Okay, so that is a whole at negative 4. Hopefully that makes sense. Okay, so that's how we find a hole. Let's look at example number 2. Here's example number 2, g of x. The first thing I'm going to do is I am going to factor and then reduce. So in our numerator we have x minus 1. X squared minus 9, that's going to give us an x minus 3 and an x plus 3. And then I have x plus 6 to the power of 2. All over, man, we got a lot of factors here. X minus 1. I have x minus 3. And just because I have a feeling some of these might pop up again, I'm going to go ahead and factor this trinomial. My first terms, if you were struggling with factoring, I'm going to split my first terms. It gives us x and x. And then 18 with a difference of 3 is going to be a positive 6. Positive 6. And a minus 3. So hey, I do have one that matches. So this is going to be x minus 3 to the power of 2. And then I have a x plus 6. Okay. So I've factored, I've broken everything down, and then now I'm going to see, okay, let's cancel some stuff, and let's see, what survives. So it looks like x minus 1, hey, those cancel, that's going to be a hole. So I have a hole at 1. I'm going to write over here, holes. Okay, then I have x minus 3 and an x minus 3 squared. So the denominator is bigger, so I still have one in the denominator. That's going to be an asymptote. Okay, I'm going to move on. What else is shared? Looks like here I have an x plus 6. We'll do pink. X plus 6. Okay, I do have one that still survives in the numerator, but because it was shared in the denominator, it is a whole. X plus 6 equals 0 gives us x equals negative 6. Okay, now I jumped over this x plus 3 here. This still lives in the numerator, and I have students asking, hey, what about those factors that are not in the denominators at all? We're going to talk about those in a future lesson, but those are x-intercepts, so you'll have a 0 at negative 3, okay? But the main idea here, what are the discontinuities we have? We have holes at 1 and negative 6, and then an asymptote here at 3. Okay? All right. Let's see if we got some practice problems here. So let's test your guys' ability. Go ahead, I want you to determine the x-coordinates of any holes for this first function. Pause the video, try this one. I'll show the answer here in a second. All right, hopefully you went ahead and pause this one and try this one. It is, once you get the hang of this, pretty easy to see holes. You're going to have holes, if they match exactly, then that is a hole. So here we have x equals 5 is going to be a hole. And then when we look at x plus 2, that is also going to be a hole. I know we do still have an x plus 2 in the numerator, but because it had a factor in the denominator, that's going to be a hole at x equals negative 2. Okay? The other one, we have a matching x minus 1, but look, the denominator has a bigger multiplicity, so we have x minus 1 to the power of 2. That's an asymptote. That's an asymptote. Those are your holes, 5, negative 2. How'd you do? Did you get it? Good job. Proud of you. Okay, let's try this one. This is going to require some factoring. I'll unpause just to double check factoring, but try this one. Try to find the holes in this one. Okay, let's go ahead and look at the factorization. The factorization may be the part that's difficult for you. In your numerator, you have a GCF. So we have x squared minus 25. This is x minus 5, x plus 5, difference of 2 squares, and then we have x plus 2. In the denominator, we always start with GCF. Do they have anything in common? That power of 3 should give you pause. Hey, what if I take an x out of everything, and then that's going to leave behind x squared plus 8x plus 15. So now I can factor this, and we get x plus 3, x plus 5. Okay, so there's the factorization. Pause me again if you need to do this, but continue on. What are the holes? All right, let's identify the holes. Shared factors. What is in common? Well, I have an x and an x squared, so there's going to be a hole there at x equals 0. Okay, and then we also have a shared factor of x plus 5, so that's going to give us a hole at x equals negative 5. Okay, so again, if you have a factor that is in the denominator that is not shared, that is an asymptote, and that's what we will explore in the back half of this lesson. But here you would have an asymptote from that x plus 3 factor. Okay, now that we've looked at how we find wholes, let's go ahead and look at some AP questions. So I have 2 multiple choice questions here that I want you guys to look at and go ahead and answer. Question 1. In the xy plane, the graph of the rational function g has a hole at x equals 6. Which of the following could be an expression for g of x? Go ahead, pause me, try this one, A, B, C, or D. All right, so which of these answers can we go ahead and get rid of right away? Well, if you understand that your hole is at 6, then that means the factor that you need shared is at x minus 6. So A and D are going to go out the window right away, and you should be looking at B and C. What they're counting on with those distractors is that you forget that the sign has to change. Okay, so x minus 6, we want a shared factor. That is not at C. The signs are opposite in C. So we throw that one out. The answer is B. Hopefully you got that. Okay, next one. Go ahead, please pause me. I want you to try this one, and this is where we will leave off. The function B is given by b of x equals x squared minus x minus 6 over x minus 3 times x plus 2 to the power 2. In the xy plane, which of the following is true about holes in the graph of B? Pause me. Go ahead, try this one. Okay, hopefully you tried that one. You did have to factor your numerator, which is x minus 3, x plus 2. So we do have a shared factor at x minus 3. The x plus 2 is going to be an asymptote because although it is shared, the multiplicity in the denominator is greater. So our answer is not going to be A or B. They say there are 2 holes there. We only have 1. C, there is a hole at 3 only because the multiplicity of negative 2 in the denominator is greater than that in the numerator. And that is true. That is true. So C is our answer here. Hopefully you got C. Okay? All right. With that, hopefully you learned about how to identify holes. In the next video, we'll talk about asymptotes and limit notation.